Now we're going to start by drawing the shear and bending moment diagrams. Since you know that your AY is acting at positive 1,000 from how we found over on this side, and you know that your BY is negative 600, and that when you have a rectangular loading, it's in a linear fashion. Then from your B to your C is going to be a constant because there's no load applied, and your CY is acting at 1,000 up. So minus 600 gets you to 400. And you go over because there is no load acting. And from here, your triangular load, you know that it'll be a parabola. So you go down to the minus 200, and you solve for that minus 200 as EY. And to get this location, we will show that later on. And same for getting your location here. Going to your moment diagram, we solved for your moment at A, and we got it to be minus 1,600. And you know that the area under your curve for your shear diagram becomes your maximum at your moment. So we solved for that, and that was 900. And then from there, you went down to 0, because you knew that little triangle area. And then you did the same here. You know that the area of this box is minus 2,400. And the area of this box is the same. It goes to 0. And then for the parabola, you know that that's derivative. We'll make it another parabolic shape. So in order to find these numbers, I will show you that now. So to find this distance here, I made an equation for the shear. I did the 1,000, which is located here, pounds, over the 5 feet that it acts, and then added the 1,000 for its, this is the mx plus b, so that would be its b. I took the derivative of that for the moment diagram, and with doing that, I factored and got the length to be 2 feet. And that's how that is located. Now to get this location here, I'm going to travel down to this, and we're going to work on this triangle right here. So this is the free body diagram of DE, and we know that this entire length is 8. But we have to cut it at this section here, so we know that's 8 minus x, because we're going to be calling this x. So in order to find this height by similar triangles, it's 8 minus x over 8 times the 150, which is the pounds per foot of the loading. So traveling down, this is now its cut shape, and with the moment diagram. So we know that, let's say if you're summing moments from this point, that and moment positive is like this, minus mx plus the 200, which is its load acting, and it's a distance of 8 minus x away. And then we also have to take into account the triangle. So this is the triangle, the 1/2 mx, or base times height, times the centroid. So with this, if you switch this equation around, you get this final mx equation, which when you in turn take the derivative of, or yes, if you take the derivative of, you get the shear moment equation. And from there, you take the quadratic formula, and you get x equals 2.33 feet. And the maximum, if you plug into this equation, is 616 pounds per foot, which will be shown on this diagram here. It's 616 pound-feet and 2.33. And that is our problem.